All right, so for the last session, we have 3 participant seminars, each half an hour duration. So the first speaker is Preeti Dubey from Department of Mathematics, BITS Pilani, and she'll be talking about modeling the intracellular pathogen-immune interaction with cure rate.
Hello everyone. Am I audible? Okay, thank you sir for giving me opportunity to attend this exciting workshop and to present my work here in this conference. So I'm going to talk on the modeling the intracellular pathogen-immune interaction with the cure rate. We have heard a lot of talk regarding this pathogen-immune interaction in morning also. Professor Ravindran has talked about the interaction between the pathogen and lot of immunology lectures we have done. So here I will cover 4 models. Step by step we have considered the different biological features to understand the better dynamics of the pathogen-immune interaction. So I'll give brief introduction. And first model, which is with the nonlinear infection rate and cure rate, then analysis of that model, and effect of absorption into uninfected cells on the first model. This is a biological feature which we incorporated in the first model. And further the analysis of that model, and then immune response, we incorporated that previous model, and we will going to study the qualitative analysis of that model. And further we consider the effect of absorption in the third model, and then some simulation results. So all of us know that what is a pathogen, and it is something which causes illness, and this is an infectious agent which can be anything like virus, bacteria, plant, fungus or parasite that causes disease in host, and host can be anything like animal, plant, fungus, and any other microorganisms like bacteria also. So this is some cartoon showing the pathogens, different kind of pathogens. So when a pathogen enter to the body, then how this react, and that we are going to learn in this one, pathogen-immune interaction. When infection occurs, when a pathogen invades body cells and reproduces, viral pathogens need the host cells to replicate, and immune system defenses against the invasion by viral pathogens. In this first line of defense is given by innate immune response, and further a specific immune response get activated, that is called acquired immune response, which provides the second line of defense, and this is specific to the antigen. Here we see that how the immune cell generated, all the stem cells are get the source of the stem cells is bone marrow, and they stem cells leads to the common lymphoid progenitor and macrophage progenitor. So macrophage progenitor gives the cells which are part of innate immune response, and this common lymphoid progenitor leads to the cells which are the part of acquired immune response, which we can say adaptive immune response also. In case of common lymphoid progenitor, there are NK cells, these are natural killer cells, and these are B cells which are called antibody cells. These produces antibody cells, and T cells are helper cells and dendritic cells. So these cells are part of innate immune response, and these are the part of acquired immune response. So here we can see that the dendritic cell and are the part of both. They are common in the both type of immune response. innate immune response it is present naturally in the body, and it gets activated when any pathogen invades to the body. And this has broadband recognition system, like it can recognize all the microbes in the body at a time. And this is not specific to any pathogen antigen. This will work for any kind of pathogen or any antigen. Here, like skin, pH, fever, these are the inflammation, these are the examples. This sir has talked in the morning that inflammation when it occurs, and then this innate immune response get activated. Acquired immune response, this comes into picture when for a specific antigens, and this has vast diversity in the sense that this can recognize different antigens in the body. Like this has a specific difference, as I earlier said that this is specific to all the antigens for specific antigens. And antibody, and the cytotoxic lymphocytes are the example for this kind of immune response. So from this cartoon we can see that what is the functionality of immune cells. Macrophages clean up viruses and call the T cells, and B cells clean up viruses and alert other B cells, and killer T cells destroy infected cells with cytotoxin. Helper T cells call for backup, and epithelial cells make up most of our body. So this model with nonlinear infection rate and cure rate, first of all I will just explain what is the nonlinear infection rate and what is bilinear infection rate. Like Anupama has explained already. This side, if we have infection, and this is HI, this is infection rate. So this rate is beta, and this goes linearly at the rate beta. It increases with the rate beta. So here we have taken for that nonlinear incidence rate beta xp. Here this should be infection, means, or here we are taking pathogen, so we can replace with p. This is 1 plus alpha p. So this term in this case it is not a linear. This will get saturated at a point which is beta by alpha. So this is the difference between bilinear and nonlinear incidence rate. Here this is the schematic diagram of the model. First uninfected cells, they will be in contact with the pathogen, and these uninfected cells are getting growth rate with lambda and dying, diminishing at the rate delta naught, and when these will interact with pathogen, this will produce infected cell by which at the rate beta, and then this infected cell may die at the rate delta 2, and here this is dying at delta 1. Sorry, this should be delta 2 and this is delta 1. So, and then this due to death of infected cell, one pathogens will be produced, and this that is the number R delta 1. So with this rate they are getting produced. That's why this is delta 1, here this should be delta 2, this is delta 1. And then we have considered the cure also. So we are giving some therapy, and then at the rate rho, then they will get cured infected cells, they will join the uninfected cell. Here are the ODE, ordinary differential equations for the model. So we can see that this here we have taken that in place of bilinear incidence rate, we have considered the nonlinear infection rate, which is beta xp upon 1 plus alpha p, and these are the initial conditions x naught, y naught and p naught. These are the parameters which we have already I have already discussed. And if we will take the bilinear, when alpha equals to 0, then this will become bilinear or linear, this incidence rate. And when there is no cure, this is studied by Burez et al. In 2005. So we have shown that this model is well posed. I am not going into that, but we have considered the basic reproduction number, which is the number of newly infected cells produced by a single infected cells when all other cells are healthy. So this reproduction number we have computed for this model, and further we have done stability analysis, and from this stability analysis we can say that the global stability from we can infer that this infection will not dependent on the initial size of the subpopulation. This is again stability analysis. I am just going to skip that. This is another model in which we have considered the effect of absorption into uninfected cells for the first model. So what is the absorption of pathogens? When a pathogen enters to the body, then this pathogen gets reduced by 1 in the blood, and this get absorbed by uninfected cells. So that time, most of the time we will ignore that. This is a small number although, but so a lot of people have ignored that. So we have considered that part. This beta xp upon 1 n plus alpha p. This is a loss of pathogens term, which we have incorporated in there. All the other things are same in this model except this term. Then we computed the reproduction number for this one also, and the stability analysis we have done. So we found that this reproduction number is, if we are going to compare, then this number is the lesser than the previous one. Further, we incorporated immune response in the model, and here this is when a pathogen enters to the body, and then immune response get activated, and that infected cell specific immune response is stimulated by this mu1 biger, and pathogen specific lymphocytes get stimulated with the mu2 pjad, and mu is the innate immune response, and mu naught is the depletion of immune response. And these are when this immune response get stimulated, and then this immune response will kill the infected cells, and this immune response is acquired immune response. This one mu1 biger and mu2 pjad, these are the part of acquired immune response. So mu1 biger, this is CTLs, and this is humoral, or we can say antibody. So this will kill to the infected cells, CTLs will kill to the infected cells, and this humoral immune response going to block the pathogens. These are the initial conditions. And here also we have tried to consider this positivity of the solutions, or the solutions are positive or not. So this shows that this our model is biologically well behaved. And we found 2 equilibrium points, that is pathogen free equilibrium point, and when pathogen is not in the body, and another is pathogen present equilibrium point when pathogen is present in the body. So basic reproduction number is dependent on the here we can say this is dependent on the immune response, and this pathogen present equilibrium will exist if this basic reproduction number RT is greater than 1. So here we have done local stability analysis and global stability analysis like others. This I am going to skip. And here in this model, fourth model, we have considered the absorption again. All other terms are same, and then this only this beta xp and 1 plus alpha p term we have considered as the loss of pathogens. So, basic reproduction number for this model is given by this expression R4, and this is also dependent on the term which we have included, absorption, and the immune response. This is K2 mu upon mu naught. This is immune term of immune response, and this is dependent on the rho also, which is cure rate. Again, we have done equilibrium analysis, so that I am going to stability analysis. I am just escaping. I'll just go through the simulation results. These parameters we have considered for the simulation. And here we can see that this starting from different initial points, I have taken from different initial points and plotted the trajectories. So we can see that we are reaching to the similar point, that is equilibrium point E1. So from this we can infer this is globally asymptotically stable, because all the trajectory are approaching to the same point, and this point is given by this one. And here also for the second model, that similar behavior we are observing, but here we can see that the number of pathogens are less than this model, because absorption, we have not considered the absorption in this model, we have considered the absorption in this model. So here number of pathogens is 10.1725, and here the number of pathogens is 7.4067. So this is quite less in comparison to the first model. And for the other two model, this is phase portrait for subpopulation of model 3. This is in XY plane, and this is in XYZ plane. This is 4-dimensional model, so I have considered two different sorry, this should be spaces, this is not plane. So different spaces I have considered for this one. So here we can see that this is all the equilibrium, all the trajectory are reaching to the E3. So in this figure we have considered that effect of beta, which is incidence rate or infection rate, we can say that on the uninfected cells and infected cells. So here when beta equals to 0, when there is no transmission of infection, when there is no infection, then we can see that all the this infected cells, uninfected cells are at their high equilibrium point, and this one is 0, it is approaching to 0. So there is no infection we can see. And for the, as we increase the infection rate, then we can see that this uninfected cells are going down, and this infected cells are oscillating, and then they are reaching to the steady point. And similar for the alpha, which is inefficient to infection, when alpha is 0, then when there is no inhibition here like this, so then we can see that there is oscillation, and they are oscillation, and we cannot say that this is stable or not. Here these trajectories will be unstable, and as we increase the inhibition, then this will these oscillations are going, and they are this infected cell is coming down, and they are approaching to the stable equilibrium point. And similarly for uninfected cells, it is going to at a higher level. In this figure we have seen that the effect of immune responses, that this one is CTS and this is humoral immune response. So when there is no immune response, then uninfected cells are at a higher level, and the pathogens are coming down first and then increasing. This means when pathogens are this decrease is due to cure rate, which we are giving. So they are at a higher level, and when as we are increasing the immune response CTLs, and then they are coming down, this infected cells are coming down and pathogens are also coming down. We can see this. And when rho cure rate we are giving, then when rho is 0, then the uninfected cells are at a some play at the means if you will compare this is a lower level, and infected cells are at a higher level. There is no therapy for the infection, and when we are giving the therapy and increasing it, then infection is coming down, and this uninfected cells are getting increased, but they are not increasing at a higher level because the therapy is given to infected cells, not to the uninfected cells. So this similarly we have drawn the phase portrait for the fourth model, and here also we can see that due to absorption here this number of pathogens are decreasing rather than that one. This one you can see here, this is the number of pathogens 6.2028, and here number of pathogens are 4.6033. And from this model we similarly that the third model we observe all the things here similar to that, but only the thing is different here that these oscillations are coming for the when we are giving this alpha 0, then these are the means oscillations are different here, and when giving this immune response it is almost similar, but we can observe the points are different here. This K1 level is different for approaching to the lower level. And in this figure we have shown the variation of rho and beta. That's we can see that reproduction number is dependent on the lot of parameters, but we have seen that this is sensitive for which parameters either. So we have shown here with the cure rate and transmission rate. As we can see that when the transmission rate is high and this cure rate is low, then the basic reproduction number for that model is high, and as this is decreasing, and when this transmission rate is a bit low, and then this rho cure rate is high, then this will decrease, the reproduction number will decrease. Here are the conclusions. We formulated 4 basic models to get an insight of host pathogen interaction and pathogen immune interaction. In the first case we considered interaction between infected cells, pathogen, and then we incorporated the absorption. So from the first one we can see that elimination of infection does not depend on the initial size of population, and in the next one when we incorporated the loss of pathogens, then we found that this can alter the stability of pathogen present equilibrium point. And further the first model is again extended to investigate the effect of innate humoral and cellular immune response on the system, and then we have shown the effect of immune responses when then there is no immune response, then density of infected cells and pathogens what get stabilized at a high equilibrium point, and in presence of immune response density of infected cells and that of pathogens what can be brought back to a lower equilibrium level. In fourth model is the extension of the third model with the absorption. It has been observed here that the density of infected cells and that of pathogens converges towards 0 equilibrium level faster in comparison to the third case. Here also we notice that the equilibrium points are globally asymptotically stable in each case, and the stability behavior gets altered in presence of immune response with the absorption of pathogens, And this is the main point which I just want to highlight. This one, we have computed the basic reproduction in each case, and we compared the relation between these reproduction number. We found that for the first model it is higher, and for the last model, which is comprises of loss of pathogens and immune response both, for that it is the least one. So we can say that this can reduce the infection if we consider the immune response and loss of absorption, loss of pathogens. And I would like to acknowledge my supervisor, is Professor Varlam Dubey. My co-supervisor is Uma Dubey, and funding agency UGC India. And thank you.
We have time for one or two questions. The question that someone would like to ask? Yeah.
Can you go back to the slide where you have shown the yeah, this one?
This one, yes.
Yeah, so basically it seems that like one can probably non-dimensionalize the whole model and get some parameter in terms of beta by delta,
yes.
And then like you can probably get some kind of simpler modification from the 4-dimensional to probably 2.
Oh yes, means we can find the 2-dimensional, and then
so basically here it seems that there is a clear relation between like alpha cure rate and transmission rate with the ratio.
I just stabilize the relation between beta and rho. I just keep all the other parameters because R4 is dependent on other parameters also. So I just try to look into that for which parameters this is more sensitive. So that's what I tried to.
Okay.
Okay, I have a question. At least I'm not sure what your notation was, but at some point you were talking about number of infected cells being 4 or 5 and so on. You had some graph where you showed the number of infected cells to be small.
Which way? Okay. This one you are saying?
So I think I'm not sure what X and Y are, but what I'm saying is that if the numbers are so small of infected cells, then stochastic effects become important. Then using an ODE approach is usually not correct if the numbers are so small. Because then you have to worry about the discreteness. I mean, you can't have half a person a cell being infected. It's 1, 2, 3, 4, 5. So that discreteness and stochasticity will both matter, is my suggestion.
Okay. Thank you, sir. But I don't know much about stochasticity. So.
Yeah. So even if your initial number of cells is small, again stochasticity will become important.
Okay.
That's another issue. Yeah. Okay, let's thank Dubey, Preeti again. Sorry. Who is our next speaker?